last time we learned about the Riemann sums. Yeah, and this was a method that we could use to approximate the area underneath the curve, right? And for the most part, other than those trapezoids, we're just finding the area of tall, skinny rectangles and adding them together, right? But what we really want is something a little bit better than an approximation. We want to know what's the exact area underneath the curve. And so really the only way to do that, if you're going to be, adding up a bunch of rectangles, is to make the width of those rectangles infinitesimally small, to a point where you have infinitely many rectangles. Imagine you had a curve that did something like this, right? Just kind of a basic curve here. And you were able to draw very skinny rectangles, like where you can't even really see the width. You could imagine you probably get a pretty good approximation, right? Those rectangles are really tiny. And so our goal today is to come up with a way to add up infinitely many rectangles. And we're going to do that with a series. And this is something that you probably touched on in pre-calculus, but let's go back over the series or the sigma notation for adding up a bunch of terms. If you didn't go over this in pre-calculus, don't worry, I'll explain it all in all. You'll be fine. But the sigma notation for a series. So first of all, a series is just a sum. It's a list of numbers that you are adding together. So you may have heard of a sequence before, which is just a list of numbers in some kind of order. And then a series is just the sum of all those numbers. Okay, so the sigma notation for a series looks like this. So you're going to draw a capital sigma, which is a Greek letter. Okay, it kind of looks like an E. Okay, that's sigma. And you're going to have some sequence. You're going to be you're communicating that you want to add up all the terms of the sequence. Okay, so we'll just call the sequence A sub k. Okay, so just some sequence. Maybe it's like k plus 1 or whatever the function might be. And then there's going to be two other pieces of information on here too. And that is which term number to start with and which term number to end with. And so we'll write those at the bottom and the top of this capital sigma. So we'll say something like k equals, and then it'll equal whatever the first term number is. So the first k, just put that there. So k equals 0 or k equals 1 or whatever the case may be. And then the number that goes on the top is going to be the last k value that we use. So let's look at a few just like real basic examples, and then we can see how we might use this to calculate the area under a curve. So here's a sequence, n squared plus 2. And what this summation notation is saying is that we want to add up all the terms, starting with the first term and ending with the fourth term. So the first term here would be just 1 squared plus 2. Okay, this is what we will call, this is our first term. This is where n equals 1. Okay? And then our second term, put that in parentheses just to make this a little more readable, would be 2 squared plus 2. Our third term, 3 squared plus 2. And our fourth term, 4 squared plus 2. And we'll stop at 4 because that's the number that you see on top of the sigma. Let me rewrite this maybe like this. So yeah, this is where we're getting n is 1, n is 2, and so forth. And so this is something you could just compute. Given a calculator would be trivial. We can, I guess this one won't be too bad. 1 plus 2 is 3. 4 plus 2 is 6. 9 plus 2 is 11. 16 and 2 is 18. So we got 9 and 11 is 20 plus, so that's going to be 38. Okay. So this is just, this fancy notation is really just a fancy way of adding. That's all it is. Just adding a bunch of terms. All right, let's do one more real quick. And then we'll get into the good stuff. So here, we're going to start with n equals 3 and work our way to n equals 5. So how many terms are we going to be adding up there? 3 of them, right? N equals 3, n equals 4, n equals 5. So when n equals 3, 3 times 3 is 9 plus 2 is 11. If I substitute in 4, 3 times 4 is 12, plus 2 is 14. And if I substitute in 5, 5 times 3 is 15, and 2 is 17. All right, so this is n equals 3. You don't necessarily need to write these, but just in case, if you're looking back at this, you want to know, where do those numbers come from? So we've got 11 and 14, that's 25, and 17, it's going to be 42. Any questions about the notation, this sigma or summation notation? All right, great. Okay. Let's think about this integral down here and see how we might interpret this as a series. All right, and this is going to be our goal today, is to be thinking about these integrals as series, as a summation, okay? An accumulation. You're adding over and over again. Okay, so we've got this curve, y equals x squared. It's a pretty basic curve here, right? Like if you wanted to envision the area that we're really trying to find here, and you have a quadratic, it's going to do something like this. Okay, we're going to go from, this is not to scale or anything like that, but just to give you an idea of what we're finding the area underneath here. Okay, who knows what it is? Okay, so before we actually start thinking in terms of series, let's go back to what we did last time, which is let's calculate this integral or estimate this integral using a right Riemann sum with 6 equal subintervals. Okay, so if we're going to use 6 intervals, how long is each interval got to be? 0.5. Yeah, half, right? Because the total interval is 3 units long. And so if we're going to divvy that up into 6 intervals, each one's got to be, half of a unit. All right, so let's maybe we make a little table here for x and x squared. And we're going to have 2. We might need a calculator for this one. 2.5, 3. 3.5, 4, 4.5, and 5. Now, or maybe we don't need a calculator. We might be able to do this. All right, so we know. Let's just write down what we know and basically go as far as we can without a calculator here. So, what's 2 squared? 4. 4. Okay. Now, if you don't know what 2.5 squared is, that's okay. It's 2.5 squared, whatever that is. Okay? If you want to throw that in a calculator, if you know that it's 6.25, that works too. But we don't need to worry about simplifying. Okay? 3 squared is going to be 9. We know that one. 3.5 squared, I don't know. If you just happen to know that 35 squared is 1,225, that's great. I'm not going to make you memorize that or anything. Okay, 4 squared. What's 4 squared? 16, okay. So basically we're just doing the easy ones, yeah? Okay, so 4.5 squared. Oh, there we go. 4.5 squared is whatever that would be. And then 5 squared, well, we know that is 25. Okay, so I want us to think about like what our final, not necessarily what like the numerical answer is going to be, but how we set up our answer. And if it was a free response question, we wouldn't worry about simplifying anyway. But if we're trying to estimate the integral, we're going to say that the integral from 2 to 5 of x squared is dx, is approximately equal to the sum of all these. So we want to be careful here. We're not just going to add these up, right? Because we're finding the area of rectangles.
4 times 2.
Something like this, So we want to be thinking base times height. The base of the rectangle is going to be this half, right? And then the height will be based on whatever the right hand of the right side of the rectangle is. So like the first rectangle's height should be 2.5 squared. What's the base length of each of these rectangles? Just one more time. Half, right? So we're going to have half. Each one of them is going to be a half, right? And so we'll add whatever 2.5 squared is, plus 3 squared is 9. And maybe just to be on the safe side, we don't even do the 3 squared. We just say 3 squared. Yeah. If you write 9, that's fine. Plus 3.5 squared, plus 4 squared, plus 4.5 squared, plus 5 squared. That would be a pretty decent estimation. Yes, sir. Exactly. The reason why we don't have the 2 squared on there is because we're using a right Riemann sum. And so that first rectangle's height is going to be based on this number. If we were using a left Riemann sum, we would, but we would lose out on the 25, the 5 squared. Okay, so we've got this sum. Let's see if we can't write this using sigma notation. Like basically, write that exact same expression, but using this new notation. How many numbers are being added up here? How many rectangles are there?
6.
Yeah, there should be 6 rectangles, right? 6 equal subintervals. And so we're going to be adding 6 numbers. All right, we'll start with the first rectangle and end with the 6th rectangle. And what we did is we multiplied base times height. And the way that I kind of wrote it in part A, maybe not the best way to translate this, but it just took a lot less space than writing 1/2 times, 1/2 times, 1/2 times every time. But each one of these terms is 1/2 times that height, right? So for each term here, it's going to be 1/2 times the height squared, and whatever this number in here is. That's really the only thing that's changing, right? The squared is there every time. So we need to come up with some expression that's going to work here. That's going to give us 2.5 and then 3 and then 3.5, 4, 4.5 and 5 and so on. I think the easiest way to come up with this expression, and this is probably going to be the hardest part of the whole thing, is just to think about like where did you start, right? We started with like our whole interval, like from 2 to 5 starts with x equals 2, right? And then from there, we just added a half to each one of these and then squared it. right? So we started with 2, but then added a half. For each increment, right? So that if we want to start with the first rectangle and substitute in 1 here, we'd have 2 plus a half. But if we want the second rectangle and plug in 2, we're going to get 2 plus 2 is 4. 4 squared would be 16, and so on. Let's just let this simmer for a minute. That sink in. Because my next question is going to be, what if we wanted to use 12 rectangles instead of 6?
Then it's 1/4 times that.
Oh yeah, sure. Yeah, go ahead.
Why wouldn't we just do it from k equals 2 to 5?
From k equals 2 to 5, and then what would go in all here?
I guess.
Oh yeah, think about that. Yeah. So we'll try to write it out and then see, like, if whatever expression you come up with is gonna be the same as this. Here's one way here's an answer for you, more clear-cut answer for you. The reason why we're going from 1 to 6 is because we are adding the areas of the rectangles, and we're going to start with the first rectangle and end with the 6th rectangle. So the k values here are really more like referencing the intervals, the rectangles, if you will. Okay. Now, the fact that we are going from 2 to 5 is that's reflected in here, maybe not so obviously yet, but I think you'll see it very soon. It's like, where is the 2 and the 5 in this problem now? And part of that has to do with the fact that we're doing 6 equal subintervals. So yeah, let's just go to C here. What if we wanted to use 12 subintervals instead of 6? How would this expression change? So yeah, so this would be 1/4, right? So where's you said that you came up with that pretty quickly. Where did the 1/4 come from?
It's 1/4 of the amount of just 1 intervals.
So yeah, so like the total, like the total base, if you will, from 2 to 5 is 3 units, right? And if we divide that into 12 intervals, we get 3 divided by 12, which is the 1/4. It's half of a half, right? So perhaps instead of writing 1/2 here, back on letter B, we might consider this, just for the sake of like seeing where everything's coming from, let's write this instead as 3/6. It's still 1/2, but then I feel like these numbers are going to be a bit more meaningful. Where the 3 is coming from the difference between the upper and lower bounds, and the 6 is coming from how many intervals you're using. So if we think about it, if we rewrite it like that, coming up with this next expression should be pretty easy, because really the only thing we're changing here is not the length that it started, but how many intervals we're dividing it up into. So instead of going from k to 1 to k to 6, I'm going to go from 1 to 12. Okay, so we're going to have 12 rectangles. The base length will be 3 divided by 12 instead of 3 divided by 6. But the rest of the expression should be the same. 2 plus 3/12 k squared. Now I want to point out where one other thing is coming from here. The 2. Notice the 2 is the same. This number is what we're starting at. So whatever the lower bound is, that's the number that should be right here. This is going to be your setup for pretty much all of these, okay? The only difference is like if you've got something else going on with your function, say it was like sine x, instead of being like this number squared, it would be the sine of that number. Okay, so this is good. We just improved our estimation, but we want to improve our estimation to the point to where it's no longer an estimation, but it's the exact value. And that means increasing the number of rectangles to infinity. Okay, so here we go.
3 over infinity.
So let's see if we can write this. Okay, so let's start with the sum. We're going to do a sum. We're going to go, we would like to go from 1 to infinity, but infinity is not a number that we can just plug into x, right? So, but what we can do is we can let this number, whatever goes up here, get as close to infinity as possible. And yeah, this means that integrals, just like derivatives, are just limits. A derivative is just a limit. So is an integral. Okay, so it's the limit as n approaches infinity of the sum from 1 to infinity. In other words, we're saying we're going to add up infinitely many rectangles where the base is 3. That's the original like distance from the beginning of the interval to the end of the interval. That's like 5 minus 2. Divided by, we can't just throw an infinity here. This is why we're using the limit notation. 3 over n, so n is going to infinity. Times 2. You got it. And this expression, this infinite limit, is the exact value of this integral. So let's just try to break it down one last time, like where all these things are coming from, okay? Because these are all the sort of pieces to the puzzle. Okay, so this right here, that's the total width. We're getting that from 5 minus 2. All right, the upper bound minus the lower bound. What does n represent?
The closest you can ever get to infinity.
Well, so like it was 6 here, it was 12 there. We want it to be infinity, so this is the best we can do. It's the number of rectangles, right? The number
Which in this case is as close as you can get.
of rectangles, yes. Where is this? Where are we going to find this 2? Where's that coming from? Like
That's the starting point.
yeah, that's your lower bound. And then everything inside the parentheses with the squared is really just the function you're working with. So this is x squared, it will be this quantity squared. Any questions so far? Okay, let's see. So we're going to try to write a limit of a series to represent each one of these integrals. So let's try the integral of x cubed from 1 to 5. Okay, so this is going to equal the limit as n approaches infinity of the sum from k equals 1 to n. So that is that they're all going to start like that. Because in each of these cases, you're trying to have infinite subintervals, infinitely many rectangles. Now the function here is something cubed. So let's just start with that. It's going to be, we're going to have a base. So just leave that blank here. And we're going to have the height of the rectangles. Okay, the height is determined by the function, something squared, or in this case, cubed, rather. Okay, the base is the distance, which in this case is 4, divided by how many subintervals you want. So it'd be 4 divided by, infinity, but we can't really do that. So we're saying 4 divided by n as n approaches infinity. All right, so what's our lower boundary here? 1. So it's going to be 1 plus 4 over n times k. Basically what's doing is this k is just incrementing by 1 each time, saying go to the next subinterval. Okay, the next subinterval, what's the height there? What's the height to the next one? And you're just adding some infinitesimally small amount each time. Saying, okay, go over just a little bit more, and then plug that in, cubic. That's the new height. Go over a little bit more, cubit. That's the new height. All right, that's it. There's your series. I don't even know if that's worth boxing. I think that's just going to make it more confusing. Okay. Any questions? All right, let's try the next one. Okay, sine x from 2 to 7. You all know what sine looks like, right? It does something like this. If we want to know the area under the curve from 2 to 7, we're going to find a limit of a series.
Why do you start at k equals 1 instead of k equals 0?
You could start at k equals 0, but then you'd have to adjust your expression instead of start. So basically, the k is like your rectangle count. We're going to start with the first rectangle. Okay. You could start with k equals 0, but that's going to complicate it a little bit because then you're going to have to basically account for moving over twice here instead of just once on that first one. I think it will complicate it a little bit. So yeah, think of that k as like your counter. Like which rectangle are we working on?
I forgot what I was talking about.
Yeah. And if you strip away the context and you just look at these expressions, it looks super confusing. Like where's all this it just does not look it doesn't look very nice. So I really want to make sure we know what each of these pieces represent. Okay. So let's think about the base. How wide is each base? Well, if the total width here is 5, and we're going to divide that into n subintervals, the base length is going to be 5 over n. And then the height is going to be whatever we get when we plug that number in to the sine function. So times the sine of, and now we just need to make sure that we're plugging in the right number into sine. And so we'll start with our lower bound 2. And then add just a little bit. Yeah. So plus 5 over n times k. Where k is that counter of okay, you're going to plug in 1 first. You're going to go over 5 over n units, where that's a really tiny, tiny, tiny amount. All right. Any questions about B?
Why don't we have an exponent?
Well, so the exponent earlier was coming from the fact that the function that we're trying to find the area underneath had an exponent. So with the first example, our function was x squared, so there's a squared. Here, our function is x cubed, so there's a cubed. Here, our function is sine x. So we have sine. It's like this thing in the parentheses is like your x. Does that make sense? Yeah, so it's just that there's no exponent in the original function. All right, part C, or letter C. So this will equal, all these will start exactly the same way. The limit as n approaches infinity of the sum from k to n, or 1 to n, the base length. So the overall distance here is 4. 4 minus 0 is 4. We're going to divide that into n subintervals. So 4 over n. And then times the height of each one of those rectangles. E to the power of, what's the first, like, our lower bound here is 0. So you wouldn't, like, if this were a multiple choice question, you wouldn't see the 0, but I'm going to write it there anyway, just so I'm consistent on how I'm writing all these. 0 plus 4 over nk. Again, normally, like, if you wouldn't see the 0 plus, but I'm going to write it there just so you see that I didn't forget to write something. It's coming from this lower bound. All right, D can be a little tricky. It looks like it's not, it looks like pretty straightforward, but there's like one little extra component to it. Yeah, of course. This is like really jumpy on me today. So this is the limit as n approaches infinity of the series from k equals 1 to n. All right, so what's my fraction going to be? What's the base length? 6 over n, good. So 6 over n times actually, I'm going to leave a little extra space in these parentheses because the function here is 2 plus x, not just x. If it were just x, we would have 3 plus 6 over nk, right? But it's not just x, it's 2 plus x. So that 2 doesn't just disappear or anything. It's still going to be 2 plus. So what can make a question like this, especially if this is a multiple choice item, a little confusing, is the 2 plus 3 is going to be simplified to 5. So if you're looking at this final answer and you're a little confused about, like, why is that first number 5 instead of 3? It's because you're adding the 2 to it, or because the 2 and the 3 got combined. So if this right here is not a typo, you'd be thinking, oh yeah, that should be 3. But no, it actually was 3. But the function here is 2 plus x quantity. That's not, I don't even have a word for that, but raised to the 5th power. All right, so let's take a look at a couple problems that you might see on the AP test that are going to look like this. And like, without, I think, really thinking about these as like adding rectangles, these questions are going to look super confusing, right? Like before today, you probably would have looked at this and be like, oh my God, there's no way I could get that. All right, so number 3. Functions given. Okay. Oh, just nice old log x, natural log. The graph of f is shown. Which of the following is equal to the area of the shaded region? Okay, I'm going to give you like a minute or two to see if you can answer this on your own. And then I'll tell you what the answer is. All right, what are you guys thinking? Anyone want to be brave enough to throw out their answer? Think it's B? Yeah, it's B. Okay. Now, this is not written the exact same way I wrote it, right? They have the base written over here, right? We've got that 3 over n as our base. That can happen. I mean, multiplication is commutative, so who knows how the AP test writers are going to put that, which order. So I think that one, yeah, that's pretty good. If you did A or B, I'm pretty happy there because you identified the correct number of interval, the correct length there on the interval. You see that there is a little bit of a difference with the natural log being outside or inside. You basically want to copy the original function and then change the x that's inside here to this expression of like lower bound plus base length times k. So if you got B there, great job. Starting to see the matrix here. Okay. Let's try one more here. Same kind of problem. No graph though. So yeah, take a minute, see if you can answer number 4. Now, what are y'all thinking for number 4? D's correct. You're seeing it. This is good. Okay, great. Okay, so let's just take it. Let's ramp it up a little bit. All right, number 5. This one is going to sound a little confusing at first, I think, but it's really not as bad as you might imagine. It says for a certain continuous function f, the right Riemann sum approximation with n subintervals of equal length is this expression. What is the value of this integral? Okay, so in order to calculate the value of the integral, how many rectangles do we want? How many? It says for, it's always going to be equal to this for n subintervals. Well, how many n's do we want? Like if we want the exact area, what does n need to be? Yeah, it's got to go to infinity, right? Okay, so n, which is the number of rectangles, we want that to go to infinity. Now, clearly, we cannot just substitute infinity into n. It doesn't work like that. But we sure can evaluate a limit, and this is going to take us back to to unit 1. Yeah. We want to find the limit as n approaches infinity of this expression. Because that expression will give us the area of all those rectangles. So this is like, maybe like day 2. I don't know. I'll have to go back and look at the calendar. Day 1, day 2, way back. How do I find this limit? As n goes to infinity, that's talking about like end behavior, or a horizontal asymptote, if you will. So you're going to look at the exponents. You're going to look at the degree of the numerator and the denominator and make your decision based on that. So let's rewrite this. The limit as n approaches infinity, what is the leading term of the numerator? Like if you're just multiplying out the first terms to get the leading term, you don't really care what all the other stuff is. What's the leading term? 6n squared, right? And the leading term of the denominator is n squared. So if the degrees are the same, if the numerator is growing as fast as the denominator, they're sort of like fit in the same category, how do we find the horizontal asymptote or the end behavior? Yeah, divide the leading coefficients. So 6 divided by 1 is 6. And there's your answer. Whew. Yeah. Okay, I think that's probably enough for today. 6, I don't think we're really going to get much more meat on that bone. Do you guys have any questions before I start passing out the homework? All right, y'all. We didn't quite get to this last problem in class. I think you'd probably be okay. You know, if we just totally skip that, you'll be fine. I think we can get away without doing this one problem. But if you really just want to complete the notes and want to make sure that you're getting this problem right, let's just go over it real quick. It says estimate the area bounded by the curve y equals 1 over x and the x-axis on the interval 1 to 3 by using a left Riemann sum with 4 intervals of equal size. You don't really need to know exactly what the graph looks like, but the 1 over x graph is our parent rational function. It does something like this. And so if we're looking at the interval from 1 to 3, let me exaggerate that a little bit so I can get a better diagram. We'll say 1 is like right here, and 3 is like over here. So we're looking for the area in here from 1 to 3. And we're going to use a left Riemann sum with 4 intervals of equal size. So the left Riemann sum means that my rectangle is going to start and do something like this. This is just a rough sketch, y'all, but something like that. Okay, so the thing is, to find the height of this rectangle, we're going to have to evaluate the function at each partition. So let's make a table. We've got x and f of x. We're going from 1 to 3, and we want 4 intervals, which means we're going to need essentially 5 partitions. Okay, so we're going to divide up. You know, there's a total length here from 1 to 3 is 2, and so if we're going to divide that into 4 intervals, each interval is going to be a half. So it's going to be like at 1.5, 2, 2.5, and then finally 3. So we're going to go from 1 to 1.5, then 2 to 2.5, and then finally 3. And we're just going to evaluate the function at each of those x values. So like if I plug in 1, I get 1 over 1, which is 1. Dealing with a decimal here is probably surprisingly going to be more difficult than dealing with a fraction, because when you divide 1 over x, you're just really finding the reciprocal. So 1.5 is equivalent to 3 halves. Okay, let me just make a note here. This is just 3 halves. And so if I reciprocate that, 1 divided by 3 halves is just going to be 2/3. Okay, 1 divided by 2 is 1/2. 1 divided by 2.5, again, I got to think of 2.5 as 5 halves. And so when I reciprocate that, I'm going to get 2 over 5. And then lastly, we get 1/3. Oh, this is jumping all over. There we go. And so if I want to find or estimate the area here, in other words, if I want to estimate this area between 1 and 3 of 1 over x dx, it'll be approximately equal to this sum of areas of rectangles. So the first rectangle is going to be half times 1, and we're using the left Riemann sum. So for that first rectangle, we're going to use 1. And we're going to basically use these 4 numbers I'm underlining here as our 4 heights. So half times 1 plus a half times 2/3 plus a half times, a half plus a half times 2/5. And there you go. Okay, we can simplify this further. You don't really need to, but yeah, that'd be a half plus 2/6, which would really just be a third there, plus 1/4. Let's see here, plus 2/10, and you could simplify that as well. But I'm just going to leave it there. All right, looks like it's going to be like a little bit over 1 probably. Part B says represent the exact area bounded by this curve as a limit of a series. Okay, so we want the limit as n approaches infinity from 1 to n. All these infinite series representations of integrals are going to start off the same way, just like that. Now, the total base here, like if all the bases added together is 2. The difference between the bounds is 2. So we're going to divide that by however many rectangles we want. Infinity, if you could plug it in. So that's the base of each rectangle. And then the height is going to be 1 over the x, okay? So we've done a bunch of these now where the x we're going to represent, because we want to start at 1. So 1 plus, then we want to increment over like a half step each time. So 1 plus 2 over n k. Okay, that's it. Just wanted to knock out that last problem. It's not much different than what we've been working on. So, if you don't get that written down, it's not the end of the world. Hopefully you still understand these integrals as series. Okay, but if you're still really struggling with this, please come in for help. I'm here to help you out, or just reach out any way you can. And that's about it. I'll see you guys next time.